Namaste and welcome to this lecture series on mathematical foundations for machine learning. We have been looking at the ideas of probability, and then we looked at random variables in the last class. We will look at some more random variables now in this class, and we will look at what is called as a cumulative distribution function, and then we will look at the moments of the random variable. So, that will be the crux of the topics to be covered for the next couple of classes. So, in the last class we looked at the idea of discrete random variables. We looked at very important discrete random variables or discrete probability distribution, where we looked at Bernoulli binomial, geometric and Poisson and equally likely and so on. And we kind of ended the class with a question like, okay, this is fine, but how do we characterize the continuous random variable. So, that was a question that we had, and what we will do is we will look at this continuous random variable and then move on to other topics. So, the focus of this class is going to be on continuous random variable. So, let us look at this. We are going to look at continuous random variables. Now, what do we mean by this? We know that in the case of discrete random variable, we had the random variable to be having a range which was finite or countably infinite. So, basically we said that a random variable whose range is finite or countably infinite is called as a discrete random variable, and then we said that okay, when we look at continuous random variable, the random variable is defined over a continuum or over an interval. Now, how do we characterize these continuous random variables? So, the question here is this. So, let x be a continuous random variable, a continuous random variable that means let us say it is defined over an interval, say a comma b. Right, this is defined over an interval a comma b. Now, what we want to do is we want to characterize this random variable, this continuous random variable. So, how do we go about doing this? Recall that if you define an interval, in an interval there are uncountably infinite number of points, right. The number of points that you have in an interval is basically uncountably infinite. Therefore, talking about probability mass of the random variable taking a specific value or the mass concentrated at a particular value of x. So, for example, I give you a comma b is equal to 4 comma 7.5, right, and then I tell you the probability of the random variable x taking a value, let us say 4.23. Now, this is going to be a very interesting value, because you have uncountably infinitely many number of points, and therefore, the probability mass concentrated at this particular point x equal to 4.23 is almost 0, right. It is, in fact, we say that this is equal to 0 because I mean you cannot really find we know that between 4 and 4.3 you have infinitely many number of points, between 4 and 4.25 there are infinitely many number of points and so on. So, it is definitely not wise to talk about probability mass function as far as continuous random variable is concerned. So, how do we, so the question still remains, so how do we go about describing or characterizing a continuous random variable? That is where we look into the idea of physics, where we say that okay, we have these where we talk about the point mass, wherever you had point mass to be equal to 0, we said that look, instead of talking about the mass, you start talking about mass per unit volume, or you look at probability I mean you look at the density, right. Instead of saying mass, just say mass per unit volume and look at density. and we have a similar situation here. So, what I would do is, instead of asking what is the probability of x taking a value 4.23, I will ask what is the probability of the random variable x taking a value about 0.3. So, what I am going to say by about is the fact that I am just going to put an interval, right. So, for example, I have this, let us assume that I have, let us say this is the random variable, the domain of the random variable, which is going to take let us say some values x. Now, what I am going to do is I am going to look at this. At this point, let us say x naught, the probability of x taking the value x naught, the random variable x taking the value x naught is 0, we just saw that. So, what do we do? We do not ask for x equal to x naught, instead we say that okay, I want it about this, I want the probability of finding x equal to x naught about this point, instead of saying x equal to x naught. Now, what I will do is I will say, look, I will take this value, I will take this value, let us say this is going to be delta x. So, I will, instead of asking what is the probability at x naught, I will ask you what is the probability about x naught. So, which means I am going to look for probability of finding the random variable x, right, within this interval, which is, let us say x naught plus delta x by 2 and x naught minus delta x by 2. I will look for this probability, and what I would say is this probability is basically what we say is, suppose if this is going to be a function which is given as say f x of x, I am going to say that it is basically area under this curve f x of x within that interval, right. I am going to tell this. So, this is going to be integral x naught minus delta x by 2 to x naught plus delta x by 2. I have f x of x dx, where I am going to give a new name for this f x of x, f x of x. I am going to call this as the probability density function, probability density function. Probability mass function we had the case of discrete random variable. Now, what we have is probability density function. So, for whenever we talk about continuous random variable, we talk about probability density function, right. So, let us look at the properties of probability density function. So, properties of probability density function f x of x. F sub x of x, right. Like we said, in the case of probability mass function, you add all the probability masses, the value turned out to be 1, that was the total probability mass that you had, unit probability mass, which got distributed to among the values, distributed among the values that the discrete random variable can take. So, there the sum of probability masses was equal to 1. In this case, we are going to say the area under the probability density curve is going to be 1. So, I am going to say this, the first property is integral minus infinity to infinity f x of x dx is equal to 1. That means, I am going to say area under the probability density curve, area under the PDF, I am going to call this as PDF, which is f x of x is 1, right. We also had one more, the very first property that we had in case of the probability mass function was the probability mass value was a value between 0 and 1. Here also we will have something similar to that. We are going to say that, look, this function f x of x must always be above the x axis. So, I am going to say f x of x is always greater than or equal to 0. It can never be below, because it is a measure of probability. The probability value can never be negative, therefore, this function has to be always positive or above the x axis. This is always above the x axis. Suppose we have like the other case where we had an event A, and then we want to find out the probability of the random variable belonging to that event A. We found that whatever the values that form the event A, you look at the probability masses concentrated in with each of those values, add all those values, and you got the probability of the event A. The same way I am going to do this. So, whatever is the interval that I am going to have defined as the event A. So, I am going to say this interval, I am going to do fx of x dx over whatever that interval that I am going to call that as event A. So, A is basically some interval which you have, interval, let us say A naught comma B naught, right, interval over this the event. So, event A is basically this. So, evaluate that with the limits, apply the limits, and then you end up getting the probability density associated with that particular, the probability associated with that particular event. So, these are a few interesting things that we have, and like how we had some very important discrete random variables. Here we are going to look at some important continuous random variables, the 3 most important of them. The first one, so some important continuous random variables. The first one that we will study would be the uniform random variable, where x is defined as uniform of within the interval, let us say a comma b. That means within the interval a b, this random variable x, when we say uniform, we will see that the value is going to remain the same across all the sub intervals that you are going to have it in this interval a comma b. So, that is what is called as uniform distribution. So, let us look at what it means. So, let us take some, let us look at that. So, x is uniformly distributed, x is uniform in the interval a comma b. Now, what does that mean? So, what do we mean by that? We have, it says, suppose I take this is my value of x that the random variable can take, and this axis is going to be my fx of x. It says that, let us say this is a and let us say this is b. So, what it says is between a and b the function is going to be constant, right. Between a and b the function is going to be constant. So, what is this function? What is this probability density function as such, right, with for this interval? So, how are we going to get this? So, let us look at that. So, we know that the area under the density curve is 1, that means the area under this curve is basically 1. Now, what is the area under this rectangle? How do you find the area under this rectangle? This is basically the length of the rectangle into the breadth of the rectangle. In this case, I am going to call this as, let us say fx of x. This particular height is going to be my fx of x. So, what do I have? I have fx of x into b minus a. The area is going to be 1, which implies fx of x is equal to 1 by b minus a for a less than x less than or equal to b. That is going to be my probability density function for a uniform random variable. The second one that we are going to look at is x is exponential In fact, this is something like what we saw in the discrete case where we said discrete uniform, where all the fellows in the range of the random variable had the same probability, we said equally likely. Something similar to that is what you have here. The next one that we are going to look at is x is exponentially distributed of say parameter lambda, right. X is exponentially distributed with the parameter lambda. So, what we are going to do is here in this case I am going to say that my probability density function is basically given by lambda e power minus lambda x for x greater than or equal to 0 and 0 for x less than 0. In fact, we can write this also here in the uniform distribution case. I can write f(x) of x is equal to 1 by b minus a, 1 by b minus a less than x less than or equal to b and 0 otherwise. So, outside of the interval this is going to be 0. So, this is what we have. So, where do we use this? This typically used to model the lifetime of a product. I am quite sure many of us would have studied when we said okay, the half life period is exponentially distributed and stuff in our class 12, we would have actually been looking at this. So, this is used to model lifetime of a product. Right. This is used to model the lifetime of a product. The other thing that we want to look at is the most commonly used and the most important of all the distributions, which is the bell shaped curve, which is used for performance appraisals in companies, for relative gradings in academic institutions and so on. We have the Gaussian or normal distribution. Gaussian or normal distribution. We say x is normally distributed with parameter mu and sigma squared, right, mu and sigma squared. So, the density function is basically given by f(x) of x is equal to 1 by sigma root 2 pi e power minus of x minus mu the whole square divided by 2 sigma square minus infinity less than x less than infinity. Okay. So, this is the density curve and it is going to look something like this. This is my mu. So, I am going to have this is plus infinity, this is minus infinity and this is my f(x) of x. Right. So, this is what it is going to be, and normal distribution is typically used in multiple places, and this is a symmetric distribution. You have a whole lot of interesting properties associated with normal distribution. But whatever said and done, if the random variable is continuous, if x is a continuous random variable, remember if x is a continuous random variable, then the probability of a sample point, that is the probability that of let us say x is equal to let us say x naught is always 0, right. For example, I tell you that look, what is the probability of x taking a value mu here. Suppose if you substitute x equal to mu here, it would become e power 0. So, that becomes 1 and then you say 1 by sigma root 2 pi. No, that is wrong, because this is the density function. The probability of x equal to x naught, a particular point is always 0, right. So, this is the most important thing about our probability density functions. Of course, you have other things like Laplacian and so on, but typically what we do is we look at Gaussian, exponential and uniform distribution and so on. Okay. Now, this if you look at either probability mass functions or probability density function, we see something very interesting. So, what is that? We say that okay, what is the probability mass function? Let me just say okay, let me. So, discrete random variable is associated with let us say x. So, as a discrete random variable, then we said the probability mass function PMF of x is equal to let us say xi is nothing but p of x equal to xi, which is equal to px of xi. That means, it is the mass concentrated, probability mass concentrated at that particular point xi, and we see that there is no, I mean the probability mass does not exist between let us say xi and xi plus 1, that it is precisely why it is called as discrete, right. You are going to have I mean you are going to have your probability mass function. For example, let me look at this. You recall that experiment of tossing a coin three times. So, recall the experiment of tossing a coin 3 times. I will make it a bit more easier. Let me take tossing a fair coin 3 times. That means, the probability of head is equal to the probability of tail, which is equal to half. Fair coin thrice, right. We have this. So, the x, the random variable x is going to count the number of heads. Let us say x counts the number of heads in 3 tosses. So, the values that x can take are no head, 1 head, 2 heads or 3 heads. These are the values that it can take. So, I can take x equal to x is basically 0, 1, 2 and 3. Now, I want to put this probability mass function here. I will say p of x equal to x, which is equal to px of x. This is what I have. If you look at the sample space in the previous case where we had the coin tossing to be 3 times, this is what we had. Here I have this probability to be out of 8 combinations, I just have one combination to come here, which is basically 1 by 8. Then we have 3 combinations to have 1 heads, which is 3 by 8, therefore, the probability is 3 by 8. There are 3 combinations which will give you 2 heads, which is basically again 3 by 8, and then there is one combination which gives all 3 heads, which is 1 by 8. Therefore, my probability values are going to be this 1 by 8, 3 by 8, 3 by 8 and 1 by 8. Now, I can't ask this question, what is p of x is equal to 1.5, because that does not even exist. Therefore, how do I graphically capture my probability mass function? It is going to be like this 0, 1, 2, 3, and let us say I am going to have something like this. This is my px of x. So, at 0, okay, let me put this here. So, at 0 it is going to be 1 by 8, therefore, let me take this as 1 by 8. There is going to be a stick here which says it is 1 by 8. Then at 1 we are going to have 2 3 by 8. So, I am going to have it here, this is 3 by 8. So, probability of x equal to 2 is also 3 by 8, and probability of x equal to 3 is basically 1 by 8. So, this is how my probability mass function is going to look like. These are basically impulses at those points where which are there in the range of the random variable, right. These are going to be just sticks or the impulses which are going to be there. However, if you look at the continuous random variable, suppose if I say look, I want to look at let us say y is a uniform random variable in the interval let us say 2.5 or let us say 1 comma 2. 1 comma 2, then the function is going to look like this, the probability density function is going to look like this. I am going to have 0 1 2. So, it is 1 by b minus a. So, f x of x is equal to 1 by 2 minus 1, which is 1 by 1. So, the interval, this is going to be 1. So, the function is going to look like this. That means it is defined at all points between 1 and 2 also. So, this is basically my f x of x, and that is going to be my x. So, the one of the most important difference that we see here is x being, if it is a discrete random variable, I see impulses at the different values of the different values that the random variable can take of different, the impulses will be of different heights. And if you look at the continuous random variable, if y is going to be okay, if y is going to be a random variable, a continuous random variable, then we have this. Okay, I just made a mistake here, let me just change that. So, this is going to be f y of y, and this is going to be f y of y, and this is going to be y. So, it is going to exist everywhere between 1 and 2, the height is going to remain the same, which is 1 by b minus a, right, done. Now, if you look at the probability mass function here and the probability density function here, all of them seem to be giving an exact representation, or it gives you exact values. For example, if I say what is the probability mass concentrated at x equal to 0, it says look, it is 1/8. What is the probability mass concentrated at x equal to 2, it says it is 3/8, and so on. Now, in case I do not have this distribution, say in case I do not have in case I do not have this information, like it is like saying, suppose I have a bank account in which I save some amount monthly, I can actually pull out my monthly savings, what is the amount that I have deposited in my account in every month. That would correspond to my probability mass function, which basically tells you exactly what is the amount that I have deposited in my account. Now, in case I do not have that information, what do I do? And that is exactly where we get into the idea of cumulative distribution function, or the CDF, cumulative distribution function, or the CDF. So, the CDF of the random variable is basically given by, CDF is nothing but capital F sub x of x. This is how, this is the notation for the cumulative distribution function. Now, what does this give me? That is the most important thing. For example, I tell you that look, I do not have the amount that I have deposited, let us say in the month of February, March, and January, February and March this year. But I tell you that look, I know the amount of money that was there in my account before, I mean by December 31st, and then I know what is the amount, total amount that I have got till March 31st. Now, I can find out what is the amount that I had deposited between this period Jan 2025 to March 31st 2025. How do I do this? You have the total amount which was deposited there in your account till January 1st. You had the amount that you have in your account which is like at March 31st, on March 31st. Now, what you do is you subtract these two guys, then the amount that you basically deposited between Jan 1st and March 31st is basically what you have. That is what we call as cumulative distribution function. So, a cumulative distribution function is also something like this. So, I am going to define f x of x as the probability of x less than or equal to say some x. This could be a bit confusing. So, what I will do is I will just change this, I will say f x of a is nothing but probability of the random variable taking a value less than or equal to a. Note that it includes the extreme point a also, right. So, it says probability of x less than or equal to a. Okay. So, the moment I say it is a probability value which is p of x less than or equal to a, all my properties of probability comes into picture. What is that? I am going to say 0 less than or equal to fx of a less than or equal to 1. Right. This is one of the most important properties. We will see what more we have in cumulative distribution function. This is the first property that we have. The second one is interesting. Suppose I tell you, look, I will take my x, let us say what is the cumulative distribution function fx of minus infinity. This is nothing but probability of x less than or equal to minus infinity. Now this is interesting because I am looking for the probability of the random variable taking a number which is smaller than minus infinity. We say that okay, minus infinity is these, you know, on the left hand side you have, that is going to be the smallest number. Now what you say is I am going to look at p of x less than or equal to minus infinity, and that is going to be an impossible event, right. You cannot have a number which is smaller than minus infinity. So that is going to be an impossible event, and therefore that probability is 0. The third property is the other extreme. We are going to look at what is fx of plus infinity. Again this x is the subscript to say that this is the random variable. Fx of plus infinity is nothing but probability of x less than or equal to infinity. This is interesting because whatever value of x that you take, it is always going to be less than or equal to infinity. So if you take the entire range, it would still be less than or equal to infinity, and therefore this is like your sample space, the event sample space, and therefore this has a probability which is 1, right. That is pretty interesting. Now the fourth one is exactly the problem that I was talking to you about. What was that? I want to look at the probability of the random variable taking a value a between the interval, I mean in the interval a less than x less than or equal to b. I want to look at this. So what is that going to be, right? What is that going to be? So how are we going to find this out? Okay, let us just look at geometrically what this means. Suppose I have, this is the point A and let us say this is the point B. Now what I have is the following. I want to figure out what is the probability of x falling in this region a less than x less than or equal to b. This is the probability that I am looking for. This is the probability that I am looking for, right. Now if you look at this interval or whatever, this a less than x less than or equal to b, I can write it in a different way. What is that? I can write this as x less than or equal to a. I will take this, I will take this set, I will take this set x less than or equal to b is nothing but I can take this as x less than or equal to a union a less than x less than or equal to b, right. I can take this, right, the entire thing x less than or equal to b is basically the union of x less than or equal to a and a less than x less than or equal to b. Now if you look at this x less than or equal to a union a less than x less than or equal to b, these two are events which are disjoint, there is nothing common to them. Therefore I can write this as p of, I can write this as p of x less than or equal to b is equal to p of x less than or equal to a plus p of a less than x less than or equal to b. Now if you look at the expression, the third term is what we actually trying to this is the term that we are trying to calculate, and therefore what I will do is I will write it this way. I will write this as p of a less than x less than or equal to b is equal to p of x less than or equal to b minus p of x less than or equal to a. Now that is interesting. What is p of x less than or equal to b? That is nothing but my cumulative distribution function of b. So I am going to write this as fx of b minus p of x less than or equal to a is basically cumulative distribution function of a. So I have p of a less than x less than or equal to b is nothing but fx of b minus fx of a. This is precisely what I was saying. You want to find out the amount that you have accumulated between January 1st and March 31st of 2025. You find out what is the amount that you had accumulated till March 31st 2025, subtract the amount that you have accumulated till December 31st 2024. That balance amount that you have is going to be the amount that you have accumulated between January 1st 2025 and March 31st 2025. So that is exactly what we are looking at here. There are some more properties here. Let us look at some more properties. So how do we come from okay, what is the nature in the first place? Let us look at what is the nature of the cumulative distribution function. So first let us look at that. So we are going to say that the CDF fx of x is a non decreasing function. Some textbook actually also give you this, they are monotonically increasing, but we will use non decreasing function because we will capture the essence of discrete random variable also. So we will say that CDF fx of x is a non decreasing function as far as discrete random variable is concerned, and it is monotonically increasing function as far as continuous random variable is concerned. So we will just put that as non decreasing function here, right. So what do we mean by non decreasing function? We know that you know the CDF is going to have something like this. The CDF is going to take say till 0, it could take a value which is say till 0 the height is 0, then at this point at x equals 0 it takes this height, and from here it takes this, and then from here it takes this, and you are going to have something like a step. So finally what we are going to say is maximum is going to be at 1. So we will say that here okay the function is going to hit 1 here, it is not going to go beyond that. So let us say this. Right, it is going to go right, that is what I am going to mark it as 1. So you are going to have something like a step function here. So this we call it as non decreasing function. This is in the case of discrete random variable, and in case of continuous random variable this is going to look something like this. So this is a continuous random variable. So this is going to be my fx of x here, and that value is 1. So here I have x here, this is fx of x, and my CDF is going to look something like this. So this is going to be 1, let us say 0 and so on, right. So this is going to increase. So this keeps increasing, you do not see this like a flat thing, it keeps increasing asymptotically, it goes to 1. So it keeps increasing now, right. So this is how the CDF for a continuous random variable is going to look like. So we say that the CDF is going to be a non decreasing function, or you can say monotonically increasing function. And the other point that we have is the cumulative distribution function. We are going to say that the CDF fx of x is right continuous right continuous. Now what does it mean? Suppose you approach the point let us say x naught from the right, then what you have is the limiting value of the CDF is going to be the value of the CDF at that particular point, say x naught. So this is what it is. So I am going to say limit x tending to let us say x naught plus fx of x is equal to fx of x naught, This is basically the idea of right continuity. Something more interesting comes up. Let us look at this here. Now, if you look at this, there is this height which is there, which is there is this difference in height that is there, right. In each of these cases you find that there is a difference in height, and now what you see is this difference in height is going to be the probability mass function P x of x. So, what are we going to say? We are going to say that for case of discrete random variable, we say that the probability mass function P x of x at P x of x is nothing but f x of x plus minus f x of x minus. So, x plus is basically a small value which is, I mean, a value which is slightly larger than x, and x minus is a value which is slightly smaller than x, right. And what we see is, like, if there is no discontinuity, I mean if the function is continuous, then f x of x plus and f x of I mean then we see that the probability mass function is basically 0. So, let us write this: if there is no, if f x of x does not have a discontinuity, then the probability mass function P x of x is equal to 0. This is exactly what we were saying, continuous random variable will have the probability mass to be 0, right. And as far as the continuous random variable is concerned, so we have this in case of discrete random variable. As far as the continuous random variable is concerned, in this case I am going to say f x of x the probability density function is basically the derivative of the cumulative distribution function in case of continuous random variable. In case of discrete random variable, I am going to write P x of x is equal to f x of x plus minus f x of x minus. Is this clear? So, the derivative of the distribution function is basically the density function. So, this is something which we have. So, in the absence of exact distribution or probability distribution of the random variable, we can also look at what we call as the cumulative distribution function, which also is a representation for the which is also used for describing the random variable. So, what are we saying? We say that in the absence of actual if you do not have the actual distribution of probability, I mean actual probability distribution, that means your probability mass function or the density function, you could still characterize the random variable using cumulative distribution function. So, that is what this boils down to. Now, we have one more question which we need to answer. What is that? Suppose I do not have, okay, let us make one statement before this and then we will get to that question. So, irrespective of whether x is discrete or continuous, the CDF exists, CDF of x, which is f x of x, exists. Now, what is the other statement we are going to make? PDF probability density function may or may not exist. Right, that means probability density function is not even defined for your discrete random variable, therefore, it does not exist. Probability mass function may or may not exist, because probability mass function is not even defined for continuous random variable. Not defined means probability mass is 0. However, irrespective of whether PDF exists or PMF exists, CDF will always exist. So, Fx of x will always exist for both discrete random variable and continuous random variable. Okay. Now, we have come to a very important question here. What is that? Suppose I do not have the distribution, I do not have the PDF, or I do not have the PMF, or I do not even have the cumulative distribution function. Can I still describe the random variable? For example, I ask you this question. Let us take the example of the city of Bangalore. I want to study the distribution of salary to working class people across all the working population that resides in Bangalore. Now, there is no way that we will be able to get this distribution, because I do not think people will be interested in spelling out their actual salary. So, there is no way that we will be able to get the actual salary distribution. Now, the question is, the salary distribution or the salary is going to be a random variable, because it is going to change with respect to profession, qualification to qualification, and so on. Therefore, it is a random variable, and I do not know the distribution of the salary. The question is, how do I still describe the random variable, which is called the salary of the working class in Bangalore. So, how do we do this? So, the question is, suppose we do not know the exact distribution say PDF or PMF or CDF. Can we still describe the random variable? Can we still study the random variable by any other means? So, that will be the question that we will be answering in the next lecture. So, in this lecture we just studied the idea of continuous random variable. We said that there is going to be a probability density function associated with this continuous random variable. We said we are going to look at cumulative distribution function. We studied the properties of cumulative distribution function and so on. Towards the end we said that, look, I may have PDF, I may not have PDF, I may not have even PMF, I may not have cumulative distribution functions, and can I still tell you, can I still describe the RV, the random variable that I have? And that will be the question that we will be seeking answer for in the next class. Namaste.